you. I would like to first, I would like to thank the organizers for giving me the opportunity to present my talk, and especially you, Suzanne, who invited me to this very nice conference. And yeah, I will present you the works I've been doing on these FitzHug-Nagumo neural networks. And first, let me give you a brief global introduction of the things we will be talking about. So our purpose here is to describe neural networks. And in order for this to be done, we consider, there are different scales at which we can describe those networks. So first, let me start with the microscopic scale, which focuses on the behavior of each individual neuron, and which can be very intricate to study when the number of neurons is large, since it contains a lot of information. Then on the left side of the picture, there is the macroscopic scale, which displays integrated quantities, so averaged, which are very interesting because they are supposed to be the ones that we can measure in experiments. So this is the scale we are interested in. And in the middle, there is the so-called mesoscopic scale, which is, so to say, artificial, since it is in some sense built in order to link the microscopic scale to the macroscopic scale. So it contains less information than the microscopic scale, but it's still quite complicated. And the purpose of the presentation is to explain you the links between in our setting, of course, between the mesoscopic scale and the macroscopic scale. So more precisely, I will study a precise regime. And we will see that in this regime, the mesoscopic scale can be approximated by an asymptotic model, which is the macroscopic one. All right, so as I told you, there are those three different scales, and let me start by introducing you to the microscopic scale. And in order to do this, I need to tell you how to model how one neuron behaves. So now I will present you how a single neuron behaves. And what we're interested in this talk, the quantity we want to study, is the voltage through the membrane of a neuron, because information in brain is propagated through voltage and variations of voltage. And so the models that we're using come back from the 50s and from the pioneer work of Hodgkin and Huxley, who built a very precise model which describes the dynamics of the voltage through the membrane of a neuron. And let me start by showing you some an illustration of these dynamics. So here, I hope you see. You can see that on the x-axis you have the time, and on the y-axis you have the voltage. So this graph represents the evolution of the voltage through time. And here on the top of the picture, you can see that there is a constant current, which is the current that is applied to the neuron, and which is constant through time. So basically what this simulation shows is the evolution, the reaction of the neuron towards a constant current. So basically they plug, you can think that they plug the neuron to an input current and see what happens. So when the current, the input is low, the neuron just relaxes to equilibrium, as you can see. But when you increase the current, you can see that there are some spikes that appear. And so the neuron spikes and then comes back to equilibrium. So this looks like what Delphine showed at the beginning. And this kind of behavior, this is the kind of behavior we will be interested in. And if you keep increasing the current, the input current, then after a certain threshold, you can see that there are some periodic behaviors that appear. So the neuron basically keeps spiking, and you have those patterns that appears. So here are the main characteristics of the model that Hodgkin and Huxley built. And now I come back to my presentation. Yeah. Okay. So the problem, so this model, the Hodgkin and Huxley model, is very precise, but the problem with this model is that it's complicated, mathematically speaking. So FitzHug-Nagumo built a simplified version, which is supposed to keep the main features that we talked about, so the spiking and the periodic behavior. And here I wrote the FitzHug-Nagumo model. So it's a couple of, it's a differential equation with two components. So the first one is VT, which stands for voltage. So it's the quantity we're interested in. And the second one is WT, which I will call the adaptation variable, and which is here to capture those periodic behavior. Indeed, if you only have one component in a first order ODE, you cannot get those periodic behavior. So the simplest way to get those periodic behavior is to add a component and you get a second order ODE, and hence you get those periodic behavior. So this is the role of this WT, and it is supposed to mimicate the gating variables in the Hodgkin and Huxley model. All right, then I need to explain you what are the coefficients of the equation. So you have these N and A, and A is a linear map, whereas N is nonlinear. So it's typically V minus V cubed. And they have in common that they are both, they have confining properties. So they bring you back to equilibrium in order to get that relaxation to equilibrium after spiking. And so here on A, the confining property comes from the fact that you have minus B with B positive, and on N you have a nonlinear confining property coming from the minus V cube, which brings you back very quickly to equilibrium, as we've seen in the simulations. And lastly, I want to point out that we added some noise on the voltage variable in order to take into account the random fluctuations of the potential, which our model doesn't take into account. So there are a lot of discussions about whether this noise is relevant and where to put it. Some people put it on the W variable, but in this talk, it's very important to have it on the V variable. Our analysis relies on this. And the external inputs, IX, represent this constant current which we plugged the neuron to. All right, so now you have the behavior of a single neuron, but we're interested in a network of neurons. So we consider now a network composed of N neurons, and we say that they interact with each other's, and their interaction is governed by Ohm's law. So now the external input that receives neuron I is given by an average of all the interaction with between neuron I and its neighbors, neuron J's. And I said that the interactions are governed by Ohm's law because you can see that you have a difference of potential here. And the coefficient that multiplies this difference of potential which tells you how strong is the connection between neuron I and neuron J, is given by an interaction kernel phi. And so this represents the conductance, and it depends on the spatial location of neuron. So you have, in fact, a spatially extended neural network, and the interaction between neurons depends on their spatial location. All right, so this is the full microscopic model. And now, let me present you the mesoscopic scale, so the intermediate scale that I've talked to you about. And it is obtained as the number of neurons composing the network grows to infinity. So on the latter model, if you say that the numbers of neurons which compose the network goes to infinity, then you can see that the dynamics of the network are well described by a distribution F. So it's F of TXVW, and it represents the probability of finding a neuron at time t and position x with a potential variable V and an adaptation variable W. And the dynamics of F are driven by this mean field equation, I call it. And so it's basically the same equation as before, but you replace the interaction term, which was a sum, by an integral, since you went from a discrete setting to a continuous one. So now, instead of summing, you integrate the interactions over all positions and all voltage and adaptation variable. And also you replace the noise by a diffusion term with respect to V. So you get a diffusion term only with respect to V, because there is only a Brownian motion with respect to the V variable. So this derivation has been made rigorously in several works and in different settings. But I won't be focusing on this part of the job right now. I want to explain you the links between the mesoscopic scale and the macroscopic scale. So I told you that the macroscopic scale is obtained in a particular regime, and let me introduce you to the regime I'll be talking about. So what we say is that the interactions between neurons are divided into categories. So the first category is weak long-range interactions. So we say that they have long range, but they are weak in the sense that this interaction kernel psi is more regular or smooth in a sense that needs to be precise. And the other type of interaction are the strong short-range interactions. So I say that they're short because the delta zero stands for direct mass. So here, only neuron at the same spatial location interacts with each others, and they are strong because there is this multiplier 1 over epsilon, and epsilon is meant to go to 0. So if we rewrite the equation with this nzets on the interaction kernel, we get the same equation on the left-hand side, and an additional term, which I put on the right-hand side, and which is the leading order of the equation with respect to epsilon, because you have a 1 over epsilon. And it displays, so this term is due to, of course, it is due to strong short-range interactions, and it displays the macroscopic density associated to the network. So there is this rho 0, which is the spatial distribution of neurons, and this capital V epsilon, which is the mean voltage at spatial location X in time t. So this is exactly what you get, and our goal here is to describe the dynamics of the network in the regime where strong short-range interactions dominate. That is when epsilon goes to 0. So let me explain you formally what happens. So in the limit epsilon goes to 0, we expect f epsilon that f epsilon should converge to something that cancels the leading order in epsilon, so the right-hand side of the equation. So that means that as epsilon goes to 0, v minus capital V epsilon times f epsilon should be very small. And this, since f epsilon is a probability distribution, this exactly means that f epsilon looks like a direct mass centered at capital V epsilon times its marginal with respect to the adaptation variable. So capital F epsilon is just F epsilon integrated with respect to V. So this, if you carry this analysis until the end, you get that F epsilon converges indeed to a direct mass centered at limiting capital V times a limiting distribution capital F with respect to the adaptation variable. And this couple capital V capital F solves a system which is a nonlinear coupled nonlinear system. So V solves the reaction diffusion equation because you have this interaction, this term here, which is an integral term with respect to the spatial variable. And it is coupled with a transport equation, which is solved by capital F. And I should mention that if you take the average, so capital W of capital F, then the system capital V capital W solves the classical, what I call classical FitzHug-Nagumo system. Okay, so this is where I started. So this is where I started. It was already, this work had already been done by Creva, Fay, and Filbé in a setting without the diffusion term. So here for this analysis, the diffusion term doesn't matter. And they proved rigorously this convergence. And so they proved basically that F epsilon concentrates with respect to the potential variable V. This is why we say that we study concentration phenomena. And now the question I tackled on that subject was to study the profile of concentration. So once you know that the voltage distribution concentrates into a direct mass, you can wonder what's the profile of this concentration. So this is basically the limiting, the direct mass is the first order in the limit of F epsilon, and the profile should be the second order. And here I just gave you two pictures. On the left side, concentration occurring with the Gaussian profile, and on the right side with the triangular profile. Yeah, so let me again formally explain you what happens. And this is where the diffusion term gets important, because this is the diffusion with respect to V is the term that drives the profile. So indeed, if this is just formal, but if we gather the leading order with respect to epsilon with the diffusion term, and we put them together, you can see that the right-hand side is cancelled by Maxwellian. So the functions that cancel the right-hand side are of the following form: exponential minus b squared, basically. So what you expect is that F epsilon will look like a Maxwellian centered at capital V epsilon with a Maxwellian with the vanishing variance, to say that it concentrates, times its marginal with respect to W. Okay, so my goal here is to rigorously justify this convergence, and I see I'm running out of time, so I will quickly present you the results. So we had several approaches to justify this limits, and the first one was what I called Hamilton-Jacobi approach. So the idea is to study what we call a Hopf-Cole transform phi epsilon of f epsilon. So you say that f epsilon is an exponential of 1 over epsilon times phi epsilon, and you want to go through the convergence analysis of phi epsilon. And basically, if you manage to prove that phi epsilon looks like a quadratic function of this type, then you're done, because if I go back here, you get exactly what was on the formal the computations. And this is what what we are doing. So this is a work in preparation that I did with Émeric Bouin. So we proved that if you take the Hopf-Cole transform close enough, very close to the limits, then this propagates with respect to time, meaning that for all time t, the Hopf-Cole transform will converge to the limit you expected, and you get the convergence with the rate. So you get a rate of convergence, which is not usual when you follow those type of approaches. But there are some disadvantages to this approach, which are that it holds in a perturbative setting. So the constraint is quite you cannot consider general initial data, and you don't see what happens with respect to the adaptation variable W, because the limit doesn't depend on W anymore. So I see. So I will now conclude, because I don't have much time left. So I wanted to explain the proof, but just to tell you that we did another approach. And this other approach, so the weak convergence, we derived. So I said that there were some disadvantages on the Hamilton-Jacobi approach. First, that it holds in a perturbative setting, and then that we don't describe the dynamics with respect to the adaptation variable. And we filled these gaps in a second result, following what I call the kinetic approach, in which we proved the full convergence of f epsilon and completed the first results that I presented you. And I will stop here. Thank you very much for your attention.
Thank you so much, Alain. Any questions?
Tell us a bit more about the proof that you wanted to talk about.
Yeah, you can do that. We have a few minutes.
Okay, thank you. Okay, so so we want to prove that phi epsilon converges to this limit. So basically, what we did, and to obtain explicit convergence rates. So basically, what we did is that we performed the Hilbert expansion of phi epsilon. So we said that it looks like the limits plus a perturbation of order epsilon. And now the proof comes down to show that this perturbation phi epsilon 1 is uniformly bounded with respect to epsilon. If you do this, then you're done and you prove the theorem. So you write the equation on phi epsilon 1, and you see that it writes like some terms that are not stiff, that are of order 0 with respect to epsilon, and some other terms that are of order 1 over epsilon. And so you guess that this operator J epsilon 1 will tell you how behaves the perturbation. And the idea was to look for the function that cancel this this operator, and then you prove that the phi epsilon 1 is bounded by building some sub and super solution to the full equation of the form phi 1, which is the function that cancel the j epsilon 1 plus or minus, depending on sub or super solution, some function that needs to be determined. So this, and then you look for the right phi, and you try to close the estimate. And once you have those sub and super solution, then you apply a comparison principle that ensures that the real solution phi epsilon 1 is in between those sub and super solution. So yeah, this is the global idea.
Oh, thank you.
If I may ask a question. So you talked about different metrics, right? So weak convergence, strong convergence,
yeah.
Wasserstein metric, I guess, and L1 or L infinity.
Yeah.
So where you lose the order, it is let's say if you dominate the weak convergence by some or the relative entropy or something like this by the strong metric, or is it somewhere coming from somewhere else?
So maybe I went, I'm sorry, I went really quickly on this this part. So the L infinity convergence, I meant the convergence of phi epsilon. So
yes.
the first result that I showed.
Yeah.
Then so there are those disadvantages I talked about, and we tried to build another method where the first thing we did is to provide a weak convergence result for f epsilon. So this is in Wasserstein metric, and you don't have those the disadvantages anymore. You don't the results hold true in for general initial conditions, not in a perturbative setting, and you say what happens with respect to the adaptation variable W. And then
and you have a better rate, right? Don't you?
And I mean, no, you still have epsilon.
Ah, then I didn't get it. Okay. But, so that's the same rate with respect to epsilon, the convergence.
Yeah.
Oh, okay.
But indeed, then it was only weak convergence. So we strengthen this result into a strong convergence, L1 convergence, which I didn't present here because we didn't have time. But with deteriorated convergence rates. So if you try to get strong convergence, you lose on the rates of convergence.
Yeah, yeah. Okay, thank you. Sorry, just a follow-up question. So you could you cook up an example where you could come up with, I mean, working on psi a little bit on the interaction kernel, where you probably ultimately would end up with a weak convergence, but not strong convergence?
So in what I presented you, the assumptions on the kernel are quite general already. So let me come back. And this is what we wanted to keep it general. Sure. In order to cover a wide range of interactions. So this interaction kernel is not supposed to be symmetric. So it's not symmetric with respect to x and x prime. And we only assume some integrability conditions on psi. So I would guess, so which are no continuous, there is no continuity required, and so I would say that it would need to be very at least very rough to not have the strong convergence because we proved it with our hypothesis. But I don't know. I'm not sure, so I can't answer very precisely.
Thank you. Thank you.
Thank you.
Okay, so I think we'll stop the session there and give ourselves a short break until the other group is ready. Maybe you want to take over, Daniel?
Yes, thank you, Suzanne, and thank you all the speakers of this very interesting session. So the other channel are telling me that they're running slightly late. So the